Have you ever seen the word pure on a food label and just kind of nodded along? Well, today we're going to challenge what that word actually means, at least to a scientist. So let's kick things off with something you've probably got in your fridge right now.
Think about it. That carton of milk probably says pure milk right on the label. But if you ask a scientist if it's actually pure, well, the answer is a whole lot more fascinating than you might think.
You see, in chemistry, the word pure has a very, very specific definition. And once you get it, it's kind of like having a secret key to understanding and classifying almost everything around us.
So let's get right to it. What does a scientist actually mean when they call something a pure substance?
This is the absolute key. A pure substance is made of just one thing. That's it. No mixing and matching. Every single particle, all the way down to the molecular level, is identical to the one right next to it. It's completely uniform. And these pure substances come in two basic flavors. First, you've got elements. These are the fundamental building blocks of the universe. Stuff like oxygen, iron, gold. You can't break them down into anything simpler. And then you have compounds. That's where two or more elements are chemically locked together in a precise, fixed recipe. The most famous example, of course, is water, H2O. It's always two hydrogen atoms bonded to one oxygen atom.
So this strict definition of pure gives us our first major fork in the road for classifying matter. Basically, everything in the universe is either a pure substance or it's something else. So let's put them head to head.
And the difference here is, well, it's night and day, right? A pure substance has only one type of particle, a fixed chemical recipe, and you can't just pull it apart physically. A mixture, on the other hand, is the complete opposite. It's just a bunch of different things physically jumbled together. You can change the recipe however you want, and you can usually separate the parts back out pretty easily.
And here's the real kicker. While we talk about pure substances a lot in science class, the reality is that the air we breathe, the ground we walk on, the food we eat, almost everything in our daily lives is actually a mixture.
So if we're living in a world of mixtures, how do we tell them apart? Well, it turns out not all mixtures are created equal. And the biggest difference really just boils down to one simple question. How well are the ingredients mixed? This leads us to our two main types. In a homogeneous mixture, everything's so perfectly and evenly distributed that it all looks like one single substance. Think of salt dissolving in water. You can't see the individual salt bits anymore, can you? But in a heterogeneous mixture, you can totally see the different components. The classic example here is sand and water. It's obvious that there are two different things in that glass.
All right, now we get to the heart of it. Within these mixtures, scientists have three key categories that we need to know. And while telling them apart can seem tricky, there's one simple secret that makes it all click.
That's it. Seriously, the size of the little particles that are mixed into the substance, that's what determines everything. How it looks, how it behaves, and what we ultimately call it.
And to help us see these different particle sizes, scientists use this awesome trick called the Tyndall effect. All it really is shining a beam of light through a mixture. And then you just ask, do the particles scatter the light, or does it pass straight through?
So let's walk through this test. In a true solution, the particles are so incredibly tiny that the light beam just sails on through without a trace. But shine that same light through a colloid or a suspension and bam! You can suddenly see the path of the beam. That's because the particles are big enough to scatter the light, making it visible. It's the exact same reason you can see your car's headlights in the fog.
Okay, so let's put this all together in one place. Solutions have the tiniest particles, they're stable, and they do not show the Tyndall effect. On the complete other end, suspensions have the largest particles. They're unstable, meaning the parts will settle out over time, and they absolutely show the Tyndall effect. And then you've got colloids, right in that tricky sweet spot in the middle. They look homogeneous and they're stable, but their particles are just big enough to scatter light.
Okay, so why does any of this matter? Let's bring it all the way back to where we started and finally crack the case of our so-called pure milk.
Based on everything we've just learned, how it looks, whether it separates, how it acts with a beam of light, what category does milk really fall into?
And there it is. There's our answer. Milk isn't a pure substance and it's not a simple solution. Scientifically, milk is a colloid.
See, it might look uniform, but what you're really seeing are microscopic little bits of fat and protein. We call that the dispersed phase, all suspended in water, which is the dispersion medium. These particles are way too small to see with your eyes, and they don't settle out, but they are absolutely big enough to scatter light. And that, my friends, is exactly why milk is white and not clear.
So the next time you look at fog or jello or even a can of paint, ask yourself, is it a solution, a colloid, or a suspension? Once you know the rules of the game, you'll start seeing the beautiful complexity of chemistry absolutely everywhere.